It's a great pleasure to introduce Associate Professor Peter Brotchie, who is a neuroradiologist at St Vincent's. And Peter and I were registrars together at St Vincent's at the time when Terry was there and Helmut was there as well. So we were all there at almost the same time at St Vincent's, I guess. But Peter has continued to do a lot of research with the Florey and with Monash. Did his PhD on basal ganglia research. He also did some research at MIT and spent some time at the Center for Clinical Data Science, which we're trying to model really the Monash Data Futures Institute and Clinical Data Science Network here at the Alfred and Monash on the MGH, Brigham and Women's Center for Clinical Data Science. But Peter has been doing a lot of AI research and work here at St Vincent's. The MRFF in AI funded, I think, 3 projects, and one of them happens to be a project that Peter is very heavily involved in. That's the breast screen project. That's St Vincent's breast screen, where they've labeled quite a number of mammograms and are developing a model for detecting breast cancers in mammography. So we're going to talk about that, as well as a few neuroradiology AI projects that we're hoping to collaborate with Peter on moving forward. So thanks very much, Peter.
Thanks, Meng. And yeah, it's a pleasure to be talking on AI. As I said, it's one of my favorite topics. All right. So yeah, so artificial intelligence, like I said, it's a great topic to talk about. It's something that's actually been around for many decades, since at least the 50s, but it's really sort of reaching some increased prominence in the last couple of years, and is now starting to influence our everyday lives. It's helping us choose what movies to watch on Netflix, what music to listen to on Spotify. It filters spam out of our emails, and it also monitors our bank transactions looking for fraud, helps us navigate with Google apps. And also, if you use things like Siri or Amazon Alexa or Google Assistant, you'll have noticed that these things can actually understand us a lot better than they could a couple of years ago. So AI basically has really started to work a lot better than it did a few years ago. And because of that, we're seeing a huge investment now in AI, and even in healthcare. If you look at publications related to AI, you'll see that in the last couple of years, there's been a huge increase in the number of publications. And the bulk of those publications are actually related to medical imaging, to radiology. So within healthcare, radiology is really at the forefront of AI research. And there's already a number of products which are on the market and which have been taken up, at least in terms of trialing, by a number of practices, radiology practices throughout Australia. And from what I've heard, most people find these products actually quite useful. So even though we're not seeing sort of widespread use of AI in the workplace in radiology at the moment, I think that we will start to see that in the next couple of years. So AI really has had a resurgence that has been around for decades, but suddenly it's actually becoming quite prominent. It's becoming quite useful and quite widespread. So, what's actually changed? Well, one of the reasons it's changed is because of this guy here, Geoffrey Hinton. He's been dubbed the godfather of deep learning. Deep learning is basically a form of artificial neural networks. And Geoff Hinton actually really became prominent in the field of artificial neural networks back in the 80s. So back in the 80s, the predominant form of artificial intelligence really was expert systems. They're rule-based systems. They're basically a bunch of, if-then statements. If this happens, then you do this. They're written in languages like Lisp and Prolog. And they had a limited usefulness. That was actually back in the late 80s. That's when I was doing my PhD. So I actually did that at the Alfred with Mal Horn, for those of you who know Mal. He had a lab set up in the Alfred Hospital in the clinical building there. And we actually worked with monkeys. So he had about a dozen monkeys actually caged within the lab in the clinical building. I don't think you'd be able to do that these days, but this was the 80s. And it was quite a good setup. They were sort of more like pets than monkeys. So every student, I was one of the students there, would have a monkey, and the monkey would sort of get to know you. And so you'd go to the cage, your monkey would come to you, and you'd let it out and walk it into its chair, and it would sit in its chair and do its task for a couple of hours while you recorded from its brain. And then you'd walk it back, give it some fruit, give it a banana, whatever. And they really were like pets. So you'd be working with them for like a couple of years, but then you'd have to chop their head off, pull out their brain, and slice it up for histology. So that's kind of when the whole pet sort of friendship sort of ended. But it was actually a really good lab. I mean, I've worked in a few animal labs, and that was actually one where the monkeys were actually really quite humanely treated. It was quite good. Anyway, I got interested in AI back then, and so I approached the Australian Artificial Intelligence Institute. That was actually within Melbourne then. I think it was in Parkville, and spoke to Michael Georgiev, who ran the institute, about what it was they were doing, and they were actually developing an AI tool for the space shuttle for NASA. And the problem with the space shuttle was it had it was extremely complex, had a lot of redundancy built into it. But if a fault occurred, it was very difficult for the pilots to know, what procedure to actually do to sort of bypass that fault. There was a manual, but it was incredibly difficult to sort of wade your way through the manual to work out, what procedures had to be done. So they developed an expert system-based type of artificial intelligence that would explain or give the pilots directions for what to do to bypass a fault on the space shuttle. And that actually proved to be quite successful. So that was a positive sort of successful form of expert system, and it was used by the Discovery space shuttle in the 90s. But really that type of AI was quite limited in general. So around the 80s as well, neural networks started to become a lot more popular. Now, neural networks were invented in the 50s, so this was like a totally different type of AI. And it was more biologically inspired, so it was based on having layers of artificial neurons, and each artificial neuron was in one layer was connected to all of the artificial neurons in the next layer. And the connections were modifiable, so they actually changed automatically based on a learning rule. And so the artificial models could be given a bunch of training examples of input and output pairs, and they would learn to modify their connections so that they replicated the particular target given a particular input. Back then, the learning rule was kind of simple. They worked very well as linear classifiers, which basically means if you've got a graph with a cluster of points, or with two clusters of points that could be separated by a line, then these networks were very good at separating out those clusters. But if you couldn't separate out those clusters by a straight line, then that's a non-linear classification problem, and these networks failed at that particular task. And once it became apparent that they couldn't do non-linear classification problems, the popularity of neural networks died off in the late 50s. And it wasn't until 1986 when Jeff Hinton, along with David Rumelhart and Ronald Williams, produced this paper in Nature that showed that you could use backpropagation as a learning rule for training these networks, and then they could solve nonlinear problems. And after this, again, the field of neural networks became very popular in the late 80s and 90s. The other major invention back then was from Jan LeCun, who developed convolutional neural networks. And this was actually a major step forward in visual processing, because instead of having every neuron in a layer connected to every neuron in the next layer, the connections between layers were via these filters, these convolutional filters. And these filters would learn their properties by backpropagation. So if you had a multi-layered network and you showed it thousands of images and it was a convolutional network, then the early stages of that network would actually develop edge detection filters, which is kind of amazing because that's, if you're designing any sort of image processing system, and the first step really is edge detection because it gets rid of a lot of redundancy in the image. But these networks, they develop that first step just automatically. They basically learn it, and it's very similar to even the visual system in animals and humans. Primary visual cortex, basically the neurons there are edge detection filters. So this is actually quite a powerful concept, and Jan LeCun used it to create models that would recognize handwritten checks in the 90s, back in the days when people actually wrote bank checks. And so he was able to sell that off to a number of bank institutes in America. But unfortunately, the computer power back then still wasn't enough to be able to actually process any sort of complex images. And so again, because of that, the popularity of neural networks again died off, and people went back to sort of more conventional forms of artificial intelligence. So for image processing in particular, they went back to sort of hand coding image feature detectors. And, it's very, very laborious, very slow progress. And the field of image processing really stagnated in the early 2000s. So because of that, there was a researcher from Stanford, Fifi Lee, who decided to try and encourage research in this area. So she developed this competition, imagenet competition. What she did was she downloaded 12 million images from the internet, and she used crowdsourcing to get all of those images labeled into 15,000 categories. Basically, the categories were, everything from airplanes, automobiles, different types of animals, toothbrushes, whatever. And then she released that in the form of a competition, and then invited labs from all over the world to participate in this competition to basically categorize, to have algorithms that could categorize what was on those images. So the first competition was in 2010, and the entrant that year had a error rate of 28%, which meant that basically it got more than a quarter of the images wrong in terms of their categorization. So not a great result. The following year, 2011, kind of a similar result, a little bit better, 26% error rate. But then in 2012, there was a dramatic reduction in error rate. And that's because in 2012, the winning algorithm that year was a deep convolutional neural network. And the entrant was, of course, Jeff Hinton's lab. I was a PhD student of Jeff Hinton. And the reason they were able to actually get a neural network to process complex images was they programmed the neural network onto a GPU, which was able to do all the computations in parallel, and so was able to actually achieve the result in a reasonable time period. So from then on, so basically this was the first time that deep learning was really sort of successful in a major competition like that. And the model has multiple layers. That's why it's called deep learning. Probably sounds better than multi-layered learning. So they're called deep convolutional neural networks. And as I said, they've evolved from a more simple form of artificial network, but now they've become incredibly complex, and they require GPUs in order to actually achieve anything in any reasonable time period. So from then on, the competition, the ImageNet competition, the only entrance into that were these deep convolutional neural networks running on GPUs. And then in 2015, the winner that year actually surpassed the human performance in this particular task. So these deep convolutional networks are actually very good at image processing. Because of the success, Jeff Hinton was taken up by Google and Yann LeCun was taken in by Facebook, and they both won the Turing Prize for mathematics in 2018. So we've got these, powerful methods for now processing images, detecting objects and classifying objects. So the question has been raised, what is that impact going to be on radiology? What's it going to be on our particular workforce? And I think, that's still an open question. But it is interesting to hear Jeff Hinton himself talk about that. So I'm just going to play a little video. Well, that's okay. What he's basically saying is we should stop training radiologists, that their day is over. But that sort of wasn't, I guess, well appreciated by radiologists, by the College of Radiologists, particularly in America, because after that was 2016. After that, there was a downturn in people actually applying for radiology training. And so there was a bit of a backlash to Jeff Hinton over that one. But I guess the good that came out of that is that a lot of the colleges then started to develop programs of artificial intelligence within the college, and a lot of radiology groups became involved in developing AI for radiology. So it actually did raise the profile within the radiology community as to what can be done with AI. And so about then, that's when St V's, when we sort of became involved as well in deep learning. And we bought a computer. We've now got about 6 computers for this type of thing with 9 GPUs. And a lot of what we do is actually to get the registrars up and running on this type of thing. So most of the registrars do 1 or 2 deep learning projects during their time at St V's. But we also have some larger projects. So we've recently started a project on detecting prostate cancer on routine CT of the abdomen. This is a project that we're doing in conjunction with a group in New Zealand and with RMIT. And hopefully we're trying to get the Alfred Hospital with Meng's group also involved in this. And the other project that I was going to talk about today is the one that Meng mentioned, which is on breast cancer on mammography, which is a project I've been working on with BreastScreen for the last year and a bit. And so what we've done with that is we've downloaded the BreastScreen database from 2014 to 2017, and we have 7,500 cases of biopsy-proven cancer. We've got the mammographic images from that, and then we have another 30,000 cases of benign lesions. And so what we've done is taken the mammograms from the cancers and those from the benign lesions, and we've just done a simple classification, basically run a few models of simple classification, classifying cancer from normals. We've had to shrink the images down a bit because the mammographic images are quite large. They're around 3,000 by 3,000 pixels, and it actually doesn't fit onto our the memory size of our GPU. So we've had to shrink it down to about 1,000 by 1,000, and then run the classification models. And so we do the training, and this is the ROC curve that we get from it. So this is from the best of the models. So an ROC curve, or receiver operating characteristic curve, is sort of probably the best indication of how a model performs. And what it is it's a plot of the true positive rate on the y-axis against the false positive rate on the x-axis. So when a model actually predicts, if you show a model an image of a mammogram, you want it to predict whether or not there's a cancer on that mammogram or if it's normal. And so the model actually predicts a number between 0 and 1. And if it predicts a 1, then that mammogram's got a cancer, or it's predicting it's got a cancer. If it predicts a 0, then it's saying that that mammogram doesn't have a cancer. And so you have to choose the threshold, because usually the number is between 0 and 1. It's not normally a 0 or a 1. And so what this curve shows is as you reduce that threshold on the left side of the graph from 1, if you look at that dotted red line, as you reduce the threshold, see if I can bring my cursor up. If you reduce this threshold down, then you get an increase in true positives, but you also get obviously an increase in false positives. So as you get an increase in true positives, then the algorithm is becoming more sensitive. So it's more sensitive towards the right side of the graph, but it's also less specific. If you have a high threshold, then the model is more specific. It's on this left side of the graph, but it's also less sensitive. So you can choose different operating points depending on how you want the model to behave. So really the sort of the best indication of how well a model performs is by taking the whole area under the curve, this area under curve. In this case, it's 0.88. So when I saw that, we had a model with an AUC of 0.88, I guess I wasn't terribly impressed, because most of the work I'd been doing before was on things like pneumothorax, where you get, models that are in the 0.9s, in the high 0.9s. So 0.88, wasn't all that impressive until I came across this paper, which shows that the AUC for a radiologist is 0.81. So that made me feel a bit better. And also their AI system that they were comparing to had an AUC of 0.84. So that kind of made our model look, not so bad. And in particular, the model is quite good in compared to like the average radiologist or the comparative model in the areas of high sensitivity. So this could be a useful model for breast screening if you take the high sensitivity operating point of the model. And so to do that, you use a low threshold. You're going for high sensitivity. In this case, it's 97%. And it gives you a pretty good negative predictive value. And the value there is that you could run this model on all of the incoming mammograms from breast screen, and you could predict which ones are most likely normal. So with breast screen, all the mammograms are read by 2 radiologists. But if you've got mammograms that you think are normal, maybe they only have to be read by 1 radiologist rather than 2, and you may not miss that many cancers by doing that. So this is kind of a proposal that we're thinking about. You can also change the model, use a different operating point with a high threshold, which gives you a low sensitivity but a high specificity. And there you're picking mammograms that you think have a high likelihood of having a breast cancer. And you could treat those differently as well. You could maybe give those to the more experienced readers or triple read them, or maybe use ultrasound. So you can stratify the mammograms based on these models, and have a more customized approach to breast screening rather than just do the same thing for every mammogram. So this is basically a summary slide showing that. So in the low risk group, maybe you could do single reads. For the high risk group, maybe you could do triple reads, or put the experienced readers on there, or combine the mammogram with an ultrasound. So we're currently running a prospective trial on this, just really looking at how the model performs on prospective data and stratifying into the 3 different groups, and basically seeing if our predictions are right, whether it is safe to just single read the low, the ones that are mostly predicted as being normal, and see if the ones that are predicted as being high risk, whether they really are coming up with a lot of cancers. So that's where we currently are, and we've used these ideas and this data basically to help us get that grant that Meng was talking about. Now, the other thing that we've done is work on localizing the actual tumor on the mammogram. So that initial model that I was talking about, that's just saying, okay, there's a tumor, or there's likely to be a tumor on this mammogram, but it doesn't say where. And sometimes maybe that's not as useful as you might think, because you want to know why the model thinks there's a tumor on that mammogram. You know, what part of that mammogram is it really concerned with? So what we've done is we've used, there's labels on this data that indicate where the tumors are on the mammogram, you know, where it is that the breast has been biopsied. And so what we've done is we've taken that portion of the mammogram, just a small area of the mammogram in that region of interest, which is encompassing the tumor. So we've got a whole bunch of these little small images that are centered on the tumor. Then for comparison, we have a bunch of images of the same size just from normal breast tissue. And when you run a classification algorithm trained on that data, then and we've got like almost 9,000 images and about 1,000 test images. Half of them are cancer, half of them are normal. When you run an algorithm on that and train it on that, then you get this ROC curve, which is obviously much nicer than the one I showed before, and it's got an area under the curve of 0.98. So this model does very well in actually characterizing whether or not there's a tumor. Of course, it's a much easier task because you're basically showing it exactly where the tumor is. So what we've done with that, though, is we have taken heat maps from that particular algorithm or that particular model. And what a heat map tells you is that if you show the model a tumor, then the heat map shows you what part of the image influences the model in deciding that that particular image contains a tumor. And so if you look at the heat map, you end up with these images here. And the heat map basically is giving you a nice outline of where the tumor is and the shape of the tumor, as you can see here. So you can use these as masks. You can create masks from these heat maps, and then you can feed them back onto the original mammogram image, and the mask actually shows you which pixels are abnormal on that original mammogram. And the value of that is that you can then train a segmentation model to actually localize where the tumor is. So typically in radiology, we use UNet models for this type of a task. And so what the UNet model does, it's very similar really to the classification model, but instead of classifying images, what the UNet model does is it classifies pixels. So what it's doing is it's outputting whether or not it thinks a particular pixel on the image is cancer or not making a judgment about the whole image itself. And you're training it by giving it a target of which pixels are abnormal. So these are the abnormal pixels, that's the area of abnormality, and you train the network to actually pick the abnormal pixels on an image. So we had 4,000 images that had masks such as this, trained on almost 4,000 and tested on almost 500 images. And the model achieved a DICE score of 0.36. Now, a DICE score is an indication of the overlap between the predicted abnormal pixels and the ground truth of abnormal pixels. So 0.36, okay, it doesn't sound great. It's like there's a third of an overlap, but it actually works reasonably well. I think one of the reasons for the lower DICE score in our particular model is it does come up with a few false positives, but in general, it actually works better than that sounds, believe it or not. But it still needs more work for sure. So I was just going to show you an example of the output of this model as it trains. So we're looking at here a mammogram from the validation set. Obviously, I'm not going to show you output on one of the mammograms that the model's actually trained on. So this is one that we're testing on. So this wasn't used for training. As you can see, there's a tumor. It's a fairly obvious tumor in this particular case with the arrow pointing at it. And if we look at the output of the model on the left is everything that's red. So this is before the model's been trained. So it's just calling everything on that image cancer. And on the right, we have the error, kind of the error. So, so initially there is, 0, which means it's doing very badly. And then it decreases down into the negatives until it gets down to 0.32, which is, or 0.36, which is the eventual dice score of the model. So if we just watch as the output of the model sort of improves as the model is training, you'll see initially it's pretty much predicting cancer almost everywhere where there's breast tissue. Then as the model trains, it's kind of concentrating more on the areas that are a bit denser or a bit more complex in terms of the breast tissue. So it's still getting a lot of false positives, but it is actually showing that area of abnormality that I pointed out with the arrow in the top part of the breast there. And then as it sort of goes forwards, you're getting less and less false positives coming through until eventually the model learns to pick just the cancer and more specifically the cancer rather than any of the other bits of high density tissue that are on the mammogram. I've got a couple of others like that. So this is the output of the model. On the left in red, you can see the pixels that the model predicts are abnormal, and on the right, that's where the tumor was. This is another example. So you can see on the right where the tumor is. It's a little bit harder to see than on that first example. But eventually the model is able to actually localize where that tumor is after fully training the model. And this is an example where the tumor is actually quite difficult to see really, but after training, the model eventually is able to localize that reasonably well as well. So the localization model does, I mean, obviously I picked out some of the better examples, but the localization model does actually work better than maybe the 0.36 dice score suggests it should. So we've got classification models for classifying the images. We've got a segmentation model for localizing the abnormality. And so this sort of formed the background work that enabled us to get an MRFF AI grant earlier this year, which was titled Transforming Breast Cancer Screening with Artificial Intelligence. And we've brought in St Vincent Institute. Obviously, Breast Screen was already involved, and we've brought in a group from University of Melbourne and University of Adelaide as well to help take this forward. And basically what we're going to do is try and improve the current models that we have. We've got the lesion classifier model, the mammogram classifier model, and we've got a model that localizes the lesion on the mammogram. So we're going to try and develop this into a sort of more unified approach and try and improve the accuracy of these models with more data and more training. And the idea really is to provide a tool for breast screen to stratify patients into risk categories. And a central component of that is going to be using AI to stratify the mammograms, but then we're also going to be using the family history and the medical history to try and make that even a bit more accurate so that we can provide also the breast screen can provide a personalized screening program rather than just doing the same thing for everybody, rather than just doing double reads every 2 years for everybody. They can stratify it so that those in a high risk group, maybe they'll get screened more often. Those in a low risk group, maybe they don't need to be screened as often. So this is sort of what has formed the basis of this particular project. So we'll be doing that for the next 3 years. I am quite aware that this is actually a neuro group. So I thought I'd better show something to do with the brain rather than just mammography. This is actually a model that I developed. It's quite an underdeveloped model, to be honest. But I had to give a talk last year for GE on stroke, and I didn't have any AI models on stroke. And I wanted to put some AI into the talk. So I very quickly developed this model. It's based on a very limited amount of data, but it's quite a nice proof of concept. And so we're going to actually take this forward. So basically, CT perfusion has become a Class 1 recommendation by the American Stroke Association, and that's based on level A evidence. And that evidence is from clinical trials of CT and MR perfusion just in the last couple of years. So the way CT perfusion works is that a patient is given an intravenous injection, a bolus of contrast while they're lying in the CT scanner. And then there's a series of CT images, usually say 24 whole brain CT images are taken at around 3-second intervals. And from that data, you're able to reconstruct these perfusion maps that give you an indication of the cerebral blood flow, mean transit time, cerebral blood volume, etc. And from that, we can work out the infarct core and the penumbra. So the ischemic penumbra is the tissue surrounding the infarct core, and it's the tissue which is at risk of progressing to infarction, but it's still currently salvageable if it's reperfused. So the main aim in stroke management is trying to prevent that penumbra from going on and infarcting. So the penumbra we can best delineate on the perfusion maps by an increase in Tmax. The infarct core is the tissue that's already infarcted, so it's already dead. And we can see that best by a marked decrease in relative cerebral blood flow. So relative to sort of normal healthy tissue, if it's less than 30% blood flow relative to normal healthy tissue, then it's already infarcted. And you can also see it in a decrease in cerebral blood volume. So in order to get these perfusion maps, the time density curves for the artery, for brain tissue, and the outflow function of contrast flowing through the veins is used. And so as the contrast first hits the brain, as it comes through the veins, or actually through the arteries into the brain, then initially what we see is an increase in the density of the arteries. That's called the arterial input function. Next, we see this increase in density throughout the brain as the contrast perfuses into the brain parenchyma, and then lastly, we see it flow out through the veins. And so you can roughly get an idea of cerebral blood volume from the area under the curve of the time density curve of the tissue. And the maximum slope of that curve gives you an indication of cerebral blood flow. But in reality, to compute these things accurately, you have to use a deconvolutional technique, and that can take quite a few minutes and a lot of computational time, because basically it's solving this equation, which you can see down the bottom. And this equation is showing the contrast in the tissue is related to these other parameters, and these other parameters, some of these we know. So we know the contrast in the tissue. We've recorded that. We know the arterial input function because we've recorded that. But what we don't know is the cerebral blood flow, well, the cerebral blood flow and the residue function. So they need to be calculated. And this operator here is a convolution between the residue function and the arterial input function. So basically there needs to be a deconvolution so that we can work out the residue function and the cerebral blood flow. And that's done by software such as Rapid. And as I say, it takes a few minutes. but you end up with these nice maps. So these maps tell you the Tmax, which is the area of tissue, which is the ischemic penumbra, as you can see in blue here. And the ischemic core is the area of tissue where there's a reduced cerebral blood volume, for example. And then you can threshold these out with the appropriate values to demonstrate the volume of ischemic core and ischemic penumbra. So the model that I developed was using the perfusion maps to give me the ground truth of where the ischemic tissue was, and then taking the voxels from that ischemic tissue and comparing it to voxels from normal tissue. We could look at the time density curves from those two different types of tissue, and you can see quite a marked difference in the time density curve for normal tissue compared to ischemic tissue. And then you can create intensity images that are based on those time density curves. And so it's a reasonably simple matter then to develop a classification network comparing the time density images, or time density curves, if you like, between normal tissue and ischemic tissue. And when we do that, and then we look at the ROC curve, we get a area under the curve of 0.94. So it works pretty well. And if we look at the prediction, then if we look at the top right here, this is the voxels that are predicted to be ischemic. We can overlay that onto the CT brain and compare it to the ground truth, and it actually works quite well. But you know, as I said, the problem is this is a limited amount of data, and so most likely won't generalize terribly well to different age patients or patients with different sort of types of arterial input functions, etc. So a lot more work needs to be done, but I think it's actually quite promising. And we have Randall Jones, who's doing a sabbatical with Meng, who hopefully is going to carry this a bit further during his sabbatical. So I think we're very fortunate in medical imaging that we are at the forefront of AI in health. We're certainly going to see some improved quality in terms of image diagnosis with the help of AI. It's already helping with improving image reconstruction. It will help with workflow. And in areas where there aren't enough radiologists, it's also going to sort of provide an expertise to help in image diagnosis in those areas as well. So it's quite an exciting field to be in, and I think an exciting time to be in radiology. So thanks for listening.
Thanks, Peter. That was excellent. We have a couple of questions in the chat, and let me go through some of them. Matt, are you there? Do you have a question about the ROI selection, going back to the when you were doing the mammogram labeling and ROI selection? Peter, did you go back to the high-res mammograms to do that? So
we were very fortunate with our data set. That's basically why we use this data set. I mean, I'm not a mammographer, so my main interest in this was the fact that the data was already labeled. So when the mammographers actually look at the mammograms, and if they think there's a cancer, they put a circle around where they think the cancer is, and that's the area that gets biopsied. So all of the mammograms had annotations on them already, and so that they're the images that I was using. So I was able to just take those annotations and use that to work out where the tumor was. So I actually didn't do any annotating at all, which is, annotating is sort of the most laborious part of training algorithms. So yeah, that was a major bonus.
Yeah, that's great. So we have actually guests from across at Monash University and from the Data Futures Institute. So if anyone has any questions from across town, please feel free to post them, or just put your hand up, I guess. Yeah, the question in the chat is, why is the ROC curve for detection of a pneumothorax less sensitive and specific than breast cancer detection from the mammogram?
Yeah, so a pneumothorax basically it comes down to subjectivity. A pneumothorax is easy to see. And so it's a lot easier for a radiologist to pick a pneumothorax than on a chest X-ray than it is for a radiologist to pick an abnormality on a mammogram. Mammography is notoriously difficult, and that's why people who do that, they get very good with their pattern recognition, looking at mammography, and that's why you need to be like specially trained to do mammography. But it's notoriously difficult, and so it's a lot more subjective compared to something like a pneumothorax, which is usually it's either there or it's not. It's usually much more obvious, and it also means that it's a lot easier. Well, it means that the data is going to be better labelled for a pneumothorax than it is for mammography, and it also means it's easier for the model to learn, which is why the ROC is going to be better for conditions such as pneumothorax than for conditions such as breast cancer on mammograms.
Yes.
So you were saying, sorry, I was just going to ask further to that, Peter. So you were saying with the MRFF grant that you're planning on hopefully trying to improve some of this? Yeah.
So one assumes that with more data, we will be able to get an improved model. And the other aspect, I guess, is the localization aspect of it. That can definitely be improved, because that was just something I cobbled together, but I'm sort of not a data scientist, so I think we can, if we put some real data science skills to work there, we can probably achieve something better as well.
Great, thank you.
A couple of questions on the penumbra project. Gerald had a question about predicting the core and penumbra from the non-contrast CT. I guess kind of like using an aspect score to which a few different companies like AI Doc and Rapid AI are doing. Is that something you're also exploring, Peter?
Like I said, that was like a super quick project that I haven't actually gone back to. I'm hoping Randall might explore that though. But yeah, I think that's a really good idea. I think, you could get a lot of information just from the raw non-contrast image in terms of the infarct core. And that may be the best way, but you could use both because we have both. So I guess it'd be a matter of using that non-contrast image plus the time density curves would probably be the best way. You may as well use all the information you have and try to get us an accurate sort of prediction of the core as possible.
Well, along the same lines, a question from Winston Chong. It says that we're doing pretty well eyeballing the CT perfusion maps that come up on Rapid in deciding whether to do the clot retrieval or not. How can AI help us improve that?
So I guess occasionally you get artifacts on those perfusion maps, like if there's a bit of movement, and sometimes the artifacts are pretty ridiculous. So one sort of hopes potentially that you'll get different artifacts with these models. Maybe they'll be less ridiculous artifacts. Maybe they'll cope with movement a bit better. And the other aspect is they should be quicker. So what often happens is, you do the CT perfusion and you've got a bunch of people just waiting around for the perfusion maps to come up before they make their decisions. Whereas, instead of having to wait for a deconvolution to actually be processed, these things should only take like a couple of seconds, really. Normally these network predictions are quite quick. So, maybe it'll just, time is brain. If you can save 3 minutes, maybe that's a good thing.
And it can also give you an answer when the interventional neuroradiologist is half asleep at 2 o'clock in the morning. This might be a good project to do across different sites.
Yeah, that's right.
And we're all doing Rapid AI and collecting this. Another question from Matt about your model for, congratulations, by the way, on getting that AI MRFF. I think there were 3 of them, and there were quite a few applications, including a few from our group that didn't get up. So obviously, I have a couple of questions that relate to that in a minute. But Matthew was asking about how the model does for DCIS, and the effect of downsampling you mentioned on your model.
Yeah, I think the downsampling probably affects DCIS more than anything. I actually, look, I haven't explored it that much, but I did remove DCIS and tested the model without DCIS, and it improved the AUC to about 0.9, I think. So it didn't make a huge difference, but it definitely works better without, if you take the DCIS cases out. And I think that is because of the downsampling. So I think it would be nice to, what I've been trying to do is train on higher resolution images. Or that's one thing I want to do, is train on higher resolution images, or maybe if even just separating out the DCIS ones and training on them separately at higher resolution. But that is I guess a concern. I haven't actually looked into how badly it performs on DCIS. I just know that the model performs better if you remove those ones from the mix. So yeah, there's still a bit of work to be done there.
Yeah, so there's a question here from Andrew from Data Futures. This is a question that will relate to your other job, your other role as a consultant to Analytics AI and Harrison AI. So for those people who don't know, Peter, besides being a neuroradiologist, is also a consultant with Harrison AI, which is arguably one of the largest startups in AI in healthcare, $29 million in Series A funding last year. So Andrew's question is the pathway for development of a platform for deployment of these workflows into the clinical setting, I guess. And maybe you can talk a little bit about how that works. And then also the partnership that this MRFF has with Harrison AI and Localizing AI.
Yeah, so I guess the difficulty of getting these algorithms into the, as a product, getting it out there so that people can use them, is it's incredibly expensive actually getting it that last step. So it's actually reasonably easy developing the algorithm to some degree, and then incredibly difficult getting that next step of getting it into a product. It actually costs millions of dollars to get through all the regulatory requirements, etc. And then also just the expertise you need to be able to interface with the different types of packs, and so putting all that together, it's actually a huge job. I couldn't believe how huge it was when I started working for Harrison or Annalise. So yeah, it does take a company with a lot of money behind it in order to get these things to the level of being a product, which in a way is kind of a shame, because there's a lot of, I guess my main interest in this is sort of the academic side of it, so I think what sort of eventually happens is that you'd have to develop something yourself to a particular level within your academic institute, and then you'd just have to partner with some group to take it the next step, to take it to a product, or partner with them, give it to them, whatever. You'd have to work out some sort of arrangement like that. I know, Meng, you must have looked into this, I'm sure.
It's not an easy thing to do. And then there are all those questions of data governance and ethical questions about who owns the data, patient ownership of the data, the institutional ownership of the data, or industry and so on. So lots of questions that are unanswered. We've got a couple of minutes left, so maybe a couple of quick questions. Helmut, do you have a question?
Well, it's kind of like a philosophical statement. Do you think, Peter, that one of the problems is that computers are just held to a higher standard than humans? I mean, you said that the radiologists had actually a lower AUC than your model, which changed the whole perspective on it. And I know that this, with self-driving cars, for example, one accident is considered an absolute disaster, whereas humans have accidents all the time. So do we need to change the goalposts here?
I guess it depends on your objective. If you want to put radiologists out of business, then we need to change the goalposts. But the goalposts are sort of protecting radiologists at the moment. it's I guess the mistakes that these models are likely to make, or that they do make, sometimes look ridiculous to us. So they may be generally more accurate. They may make less mistakes, but then when they make one, because they're working, they're processing this in a kind of a different way to the way we do. The mistakes can be quite ridiculous. If they come across a case that they haven't seen before, that the model hasn't been trained on, then it could come up with a ridiculous answer. Whereas, a human will tend to see something they haven't seen before, and they'll either try to work it out and come up with something that's logical, or they'll admit that they've never seen it before. The models won't say they've never seen it before. They'll just come up with a ridiculous answer. And so that can really, make them look, make people lose faith in them, basically. So that for the time being, you would think there's always got to be a human sort of involved to at least stop those sorts of things. But, the question is, does that human have to be a radiologist? Could it just, be the referring doctor? That's a question I don't think I want to ask, actually. But it's probably out there.
It has to be a radiologist, not a neurologist, Peter. That's very important.
Well, I think that's obvious. I think that's so obvious. Yeah.
Well, I'm cognizant of the time. It's 1:30 now, and there's a couple of questions outstanding which we didn't get to from Duong and from Zaolin. I'm sorry, guys, but you can probably email Peter or email myself. And I think this is obviously a very topical topic for discussion, and we're hoping to have more of these in collaboration with Monash University, Alfred Health, and the Data Futures Institute. So we're hoping to have more speakers that can talk about data science, particularly clinical data science and AI, and hopefully get involvement across campuses. So thanks, Peter. That was an excellent talk. Lots of questions and still a lot more on the chat. And hopefully we can get together. And people who want to collaborate with some of these projects, please feel free to send an email to Peter and I, and we can perhaps get people together on these collaborations. So thanks a lot again, Peter, for your time.
Okay, thanks, Ben. That was a pleasure.